The infamous dot product. Most students actually know how to calculate the dot product with ease. But today in this video, I want to dissect what we're actually doing because I don't think I knew until way after I learned about the dot product. So dive in with me and let's figure out what the dot product actually is and why we're doing what we're doing. Hi, my name is Danielle, and if you're new around here, I'm a high school math teacher. And here on this channel, I love to share my lessons and give strategies so learning math feels easy for students. So if you're a high school math student, then definitely hit subscribe down below. Okay, let's dive in. Okay, so here we are, the dot product. What we know so far is that a vector plus a vector will equal a vector, and then a scalar multiplied by a vector will give us another vector. What we haven't really explored yet is what happens when we do a vector times a vector. Now, this can be interpreted as just determining the directional growth or directional multiplication of the two vectors. So we want to essentially multiply what's common or look at where the overlap is for all vectors involved. Now, there are two types of multiplication that we will look at this level. In today's lesson, we're only going to cover one, the dot product. But the two types are the dot product, which is A dot B, sometimes called the scalar product because it results in a scalar quantity. And then there's the cross product denoted by A cross B. And sometimes that's called the vector product since it results in a vector quantity. Now, to help us visually see what the dot product is, I put this diagram together. And imagine you had vector A with components AX, AY, and AZ. And then vector B has the same idea. So components BX, BY, BZ. Now, if we are looking at the directional multiplication or directional growth, what's going to happen is think of distribution. Everything's going to multiply with everything else, which is what we're seeing here in this diagram. But for the dot product, we essentially only care about the components that are the same that are multiplying together. So AX with BX, AY with BY, and then AZ with BZ. Those are going to be the three pieces of multiplication with a vector in 3D, of course. We'll adopt this for a vector in 2D. And then we'll add those to get the full answer for multiplication. So let's go down here. Okay, where we have for the dot product, if we have vectors A and B, each with their components, AX, AY, AZ, and BX, BY, BZ, we care about the movement in the same direction. So we will multiply only the components that are going in the same direction, like I showed up above, the X with the X, the Y with the Y, etc. So for the dot product, we are going to say that we have AX times BX plus AY times BY plus AZ times BZ. And after you add them all up, that is considered the scalar quantity for the dot product. Okay, let's try making sense of it a little bit further. So let's talk about directional growth between two ordered pairs. So working in 2D with 3, 0. So 1, 2, 3 is here. So that's our first vector. And then let's change colors. We have vector 4, 0. So 1, 2, 3, 4, which is right here. And if you look at them visually, they are going in the same direction. So 3, 0 and 4, 0. Let's say if we're thinking about this in terms of bearings, it's north, south, east, and west. They're both going in the east direction. So the directional growth is going to be the 3 times the 4, 3 times 4, plus the 0 times the 0, which is just 0. So our directional growth is 12. Now, what if we were to compare that to the vectors 3, 0, which we already have here on the graph in orange, and then the vector 0, 4. That's not going in the east direction, rather that's going in the north direction. So that would be going vertically up 1, 2, 3, 4 to, let's say, right there. There is no overlap. There's no common direction between those two vectors. So that would actually result in a dot product of 0. So to elaborate on that idea, what I want us to do is think of the dot product in terms of distribution. I call it a square dance for vectors to help make it sticky. When you're square dancing, you will go between different partners. I know that sounds funny, but you don't necessarily stay in the same stay in the dance with the same partner. So what we're going to do is, and I don't know why my vector symbols are not turning up here, but this is vector A and B. But given these two vectors, if we want to find their dot product, then what we're going to do is think about them square dancing. So distributing. So here, let's look at vector A. Vector A can be broken down into its horizontal and vertical components. So this is vector A, and it has its AX and AY components. Same with vector B. It has its BX and BY components. What we want to do is take the AX component and multiply it to the BX and to the BY component. When you do it to the BX component, you have XX, which means they're both going in the same direction. That's good. That's what we want. However, when you do, now where is it? AX times BY, it has no direction that's the same. So it's going to cross out and go to 0. Okay. The same is true for AY and BX. Here, it's going to go to 0. But AY and BY, when they multiply, they're both going in the same direction. So that's good. We're going to get a quantity for that. So essentially what this means is our dot product will be the multiplication of AX and BX components, adding to the multiplication of AY, BY components. So if you are in R2, you will deal with just 2 components. If you're in R3, and again, I don't know why my vector symbols are not showing up, you will deal with 3 components. Okay? Sorry, I have to fix this. It's driving me crazy. All right. Let's look at this with an example. If we have vector U with components 3, 0, -1, and vector V with components -2, 5, 8, you can multiply. So then you get the 3 and the -2 multiplying. You get the 0 and the 5 multiplying, and you get the -1 and the 8 multiplying. So this becomes -6 plus 0 minus 8. So -14 is going to be your dot product. Okay, now let's think about it in terms of rotation. By rotation, or by rotating the two vectors such that one lies horizontally, it doesn't actually change anything. So we're going to do this and try it with vector A and see how it breaks down into its horizontal and vertical components so we can actually see the overlap and calculate it. So let's look at vector A and vector B here. Vector A, vector B. If we rotate vector B down, so that way it's flat on a horizontal, vector A is going to rotate down with it. And it's still going to be the same vector. Nothing has changed. Just the positioning of it has changed. Okay. So what we want to see is what horizontal overlap, because this is the part that's the same direction or going in the same direction as vector B. We want to take that horizontal overlap right here or horizontal component of vector A and multiply it to vector B. So this is the piece that we're looking for. We're looking for the horizontal overlap. The vertical overlap has no common direction, so we're just going to wipe it out. Okay, how do we calculate that horizontal overlap? Well, if you think about it, this is a right angle triangle, and so this is really our adjacent side. So what we need then for the dot product is we need our magnitude of our adjacent side. We don't care about the direction of it. We just need the magnitude of it times the magnitude of vector B. Well, how do we find the adjacent side? Well, the adjacent side, if it's a right angle triangle, is going to be cos theta equals magnitude of adjacent side all over the magnitude of the hypotenuse, which is just vector A. we can isolate for this. This is going to be vector A if we cross multiplied times cos theta. That's what the adjacent side is, the magnitude. So here I can replace this adjacent side with A cos theta times magnitude of B. Now, in textbooks, you're going to see it cleaned up and written as magnitude of A times magnitude of B times cos theta. So I hope this brings to light what you're actually doing and why, because we're going after that directional growth. And the directional growth comes from the overlap of vector A, its horizontal component, multiplied with vector B. Let's piece this together in a nice, easy question for you. So if we have vector A with a magnitude of 5, and we have vector B with a magnitude of 6, and the angle between it is 45 degrees, we would like to find the dot product of the two. So A dot B is equal to, like we said up above, magnitude of A times magnitude of B cos theta. So we know 5, 6, cos 45. I'm going to use special triangles here. So we're going to get 30 root 2 over 2. And so that's just going to be 15 root 2 units. And there you have it, dot product. Are you as fascinated with the dot product as I am now? I know, it's pretty cool, right? I hope you enjoyed that video. Hit like and subscribe if you did. And if you have anything else you'd like me to cover, definitely comment below and I'll try and do it in my upcoming videos. I'll see you in the next one.